All right, on the worksheet called In-Class Momentum, we're going to take a look at two problems. We're going to be on the back side of the worksheet called In-Class Momentum, and we're going to look at question number 6. So on In-Class Momentum, question number 6, we're going to look at these problems. Now, from here on out, what we've kind of been dealing with are on our equation sheets. Our equation sheet. Our momentum section is over here. And we've been dealing with the first three equations within momentum. Yesterday we started talking about the fourth. From here on out, we're going to be mostly dealing with that fourth equation. And that fourth equation is called conservation of momentum, and it really says that all the momentum that we start with has to equal all the momentum that we end up with. That's what conservation of momentum says. So, how do we know when to use the first three equations versus the fourth equation? The first three equations are really used when we have one object, and we really are only focusing on that one object. So, on the worksheet from yesterday called Momentum and Collisions, the whole front half was those types of problems. It was talking about like the Titanic hit an iceberg, but it was only talking about the velocity of the Titanic, it was only talking about the mass of the Titanic, it was only asking about what is the final velocity of the Titanic. So yes, there was a collision, yes, there was an interaction, yes, there was an impulse, but it was really only dealing with the Titanic. The very last problem, it's cue ball and 8 ball. Yes, that is two objects colliding together. However, a force was given, a change in time, the time of impact was given. So equation number 3 is the only equation that has a force on it. So yes, it is two objects colliding with one another, but there's enough information that we are only talking about the 8 ball. Okay, we're worrying about that. So, the two problems we're going to do today are similar to the two problems we did yesterday. And they're going to be types of collisions or interactions from this little slip of paper yesterday. So, a couple of times I'll just kind of start getting us in the habit of what kind of collision or what kind of interaction is this. So, number 6 on the worksheet called In-Class Momentum. A 10,000 kilogram semi is sitting at a stoplight. A person driving their 2,000 kilogram car is looking at their phone and they don't see the semi stop. If the car was initially traveling at 12 meters per second and they lock bumpers, all that's saying is they collide and they stick together. They're locked together and they move off together as one object. Okay, they get stuck together. That's what I mean by lock bumpers. How fast do the car and the semi move after the collision? Because they're going to be moving together as one object. So pictures, I feel, are pretty helpful. I have a car, object A, I'm just going to say is the car, and it's traveling towards a semi, which is object B. I'm choosing the car to be moving to the right. Could you say that object A is the semi? Sure. Then just make sure object B, your car, is moving towards the semi, which would be a negative velocity. It's fine. It's just how I'm drawing my picture. After the car collides with the semi, they lock bumpers and they get stuck together and they move off together as one object. It's two different objects. It's two different objects that are in a collision or an interaction. There's a location 1, there's a location 2. It's really the before and after, right? A before the collision and an after the collision. So, when we use that fourth equation, and I'm going to write it, we're not, maybe just to kind of point at, when we use that equation, we're going to need to know momentums. I'm going to need to know the momentum of this, and this, and this. So, in order for me to calculate the momentum, remember momentum, I have it written over there, is nothing more than mass times velocity. So, if I need to find the momentum of this, and this, and this, then I find it very beneficial to label my picture with the mass and the velocities of each and every item at each and every location. Because this kind of builds my formula for me by doing it this way. So rereading the question, Make sure you put your mass in the right spot and your velocities in the right spot, but it says that a semi has a mass of 10,000 kilograms. My semi is object B, is sitting at a stoplight, which means they're not moving. Your velocity is 0. A car with a velocity, a mass of 2,000 kilograms is moving, according to my picture, with a positive velocity of 12 meters per second. Because I drew my car moving to the right, positive velocity. If they lock bumpers, meaning they get stuck together, their combined mass is going to be 12,000 kilograms, and it's asking how fast will they move off together after the collision. Conservation of momentum says the momentum of this plus this, these are my befores, added together, equals my momentum of this afterwards. I'm going to use that fourth equation in our momentum section, and that's conservation of momentum, where sigma, sum of, p, momentum, 1 before the collision, is equal to sigma p2, the sum of my momentum, number 2, after the collision. Again, I think that drawing this picture helps build this equation. Because sum of all my momentums before, I start with 2 objects, which means I need 2 momentums that I'm going to add together. I have the momentum of object A before, that's this object, and I have to add that sigma sum of object B before, and this equals the sum of all my momentums afterwards. I end up with 1 object, so I have 1 momentum, and that's object AB, and it's going to be after my collision. Again, this picture is really just saying the momentum of this plus the momentum of this equals the momentum of this. That's what that picture is is showing us for conservation of momentum. I guess it doesn't show us, but momentum, how do we calculate momentum? What's our formula?
Mass times velocity.
Mass times velocity, yeah. So how do we find the momentum of object A before the collision? Well, I take the mass of object A, and I multiply by the velocity of object A before the collision. I take the mass of object A, and I multiply by the velocity of object A before the collision. That's how we find this. This times this. Plus, momentum of object B before the collision. I take the mass times velocity. I take the mass of object B times the velocity of object B before the collision, this times this, equals the momentum of this, mass of AB times velocity of AB2. Momentum is mass times velocity, so mass of AB times the velocity of AB2, this times this. Our problem set up now is just plugging in numbers to solve. Identifying what we start with, identifying what we end up with, interpreting what is given and what we know, building our equation. Now it's just algebra. My initial velocity of B was 0, so it means B had no momentum. The semi was sitting at a stoplight. It doesn't have momentum. If we take the mass of A, 2,000, multiplied by the velocity that that car had before the collision, positive 12, that's equal to the combined mass, 12,000, times VAB2. 2,000 times 12 is 24,000, is equal to 12,000 VAB2. Divide both sides by 12,000. VAB2 is equal to positive 2 meters per second. The semi is going to move positive to the right, 2 meters per second. So they're both going to move to the right. The car is going to slow down considerably, the semi is going to move forward because it will have gained some momentum. The car will have lost some momentum because it collided with the back end of it. What kind of collision is this? Is it a recoil inelastic, elastic, or potentially partially inelastic? How'd they start? Apart. So these are my three parts. How did they end? Together. So it's an inelastic collision. This is an inelastic collision. Start apart, end together. Now what happens if they would have bounced off of each other? Well, then it's one of these last two. They started apart and apart. That would be a different problem. Questions on that one? All right, we're going to do one more problem, and then I'll give you some work done. We're going to take a look at problem number 7. Problem number 7 is a problem that's a little bit different than your typical two-location collision problem. And we'll kind of talk this through. So we have an 80 kilogram student decides to go tubing in their backyard down a 5-meter tall frictionless hill. Since her parents are concerned about her safety, they put a 40 kilogram hay bale at the bottom to stop her before she collides with a tree. If the hay bale does in fact stop her, how fast will the hay bale fly up? And then what type of collision is this? So we start with the person going down a hill, they hit a hay bale. Okay, so they start apart or together. Apart, and then the hay bale goes flying away and she stops. So they start apart and they end apart. So it's either elastic or partially inelastic, right? It's one of the last two. At this point in time, we can't necessarily clarify which one of the two it is. I have reason to suspect that it's probably a partially inelastic one, just because we probably lost some kinetic energy along the way. But without actually doing that calculation, I don't know, and I'm not asking you to do that at this point. So before we set up this picture, it's going to be a picture kind of like this. We start with two objects, but we end with two objects. We need to know mass and velocities before. We need to know mass and velocities of every object after. So let's just kind of do a checklist. Do you know the mass of the tuber, the student? Yes. Do we know how fast she was going before she collided with the hay bale?
We can find out.
Okay, we don't know it right now, right? So unknown. We have one unknown. Do we know the mass of the hay bale? For the record, I'm asking about masses and velocities because that's how we calculate momentum, right? So do we know the mass of the hay bale? Do we know the velocity of the hay bale before she collides?
Yes.
Yeah. Okay. 0, right? It's sitting there. Okay. So then she hits the hay bale. Do we know her mass still? Yeah. Do we know her new velocity after she hits the hay bale? Yeah. She stops, right? Do we know the mass of the hay bale still? Yeah. Do we know the final velocity of the hay bale? No. Okay, so we have two unknowns. We have two unknown velocities. We don't know her velocity before she hits the hay bale, and we don't know the velocity of the hay bale after she hits the hay bale. The question is asking about the hay bale. Okay? So the intent of this problem is to solve for the velocity of the hay bale, which hopefully is a hint that we can calculate the velocity of the tuber before she hits the hay bale. Now, if she's on the top of a frictionless hill and she slides down the frictionless hill, she's not pushed down the hill, she simply slides down a frictionless hill. How could we calculate her velocity at the bottom of that hill?
Mechanical energy.
Mechanical energy, yeah. Okay, so we are actually going to have to do a little bit of calculations from last unit. Not a whole lot, this doesn't happen very often, but we are going to do a quick problem like that. In this situation, it's a two-location problem. The top of the hill versus the bottom of the hill. So at the top of the 5-meter tall hill, she's going to have an h of 5. At the bottom of the hill, she's going to have an h of 0, right? She's at the bottom of the hill. If we want to know her speed at the bottom of the hill, v2, we can do an energy equation. And then we'd also have to know her v at the top of the hill. Now, it doesn't directly say it, and maybe I should be more clear. But generally speaking, how fast are you going at the top of a sledding hill?
0.
0, okay? So that's probably not, we'll go with it. I probably should be more clear, but that's that idea. We can solve this with work and energy. Now, this is not a momentum problem. This is not a momentum calculation yet. This is a work and energy. So when we do this, it's a two-location problem. It's a work in plus work done by friction is equal to our change in mechanical energy. Is there any work in? How come? How do I know?
She's not pushed.
She's not pushed. Yep, no applied force. Is there work done by friction?
Nope.
How do you know?
Frictionless.
Okay, so this is that special type of two-location problem called conservation of mechanical energy, where ME1 is equal to ME2. Okay, now we fully expand this out to do a bunch of cancellation, but the idea of ME1 is PEG1 plus PEE1 plus KE1 is equal to PEG2 plus PEE2 plus KE2. That's ME1 equals ME2, remember. What question do we ask ourselves for PEG? Is there a height? For PE, is there a? And KE, is it moving? So using those questions, is there a height at location 1? Yes. Is there a spring at location 1?
No.
Is it moving at location 1?
No.
At location 2, is there a height?
No.
Is there a compressed spring? Is it moving?
Yes.
Yes. So this simplifies quite nicely. PEG MGH1 plus 0 equals 0 plus 0 plus 1/2 MV2 squared. And I can solve for V2. She's 80 kilograms. 80, 9.8, 5, 1/2, 80, V2. Okay, now some of you might say, hey, I have a mass in every single term on both sides of the equation. Can't we cancel that? And the answer is yes, you could. But I'm not going to. So 80 times 9.8 times 5 is 3,920, which is equal to 40, 1/2 of 80, V2 squared. Square root of both sides. Oops, don't do the square root yet. Oh, I almost made a math mistake. Oh, we could have done it, but most people screwed the algebra. I probably would have too. Okay, well, we should divide by 40 first, shouldn't we? We should. Yeah, absolutely. Okay, so we divide both sides by 40. Now we get 98 is equal to V2 squared. Now we want to take the square roots of both sides. And we get a V2 of 9.89949990 meters per second. Okay, so that's how fast she's going at the bottom of the hill. So if that's how fast she's going at the bottom of the hill, how fast will she be going when she hits the hay bale? Remember, it's frictionless. She's going to be going that speed, okay? So now we can deal with a momentum problem. Now I can say, hey, look, I have a person on a tube who's traveling towards a hay bale. They hit the hay bale, so that's before they hit the hay bale. After they hit the hay bale goes flying off. Okay? So that's now what we're dealing with. So I start with two objects, I end with two objects, I start apart, I end apart. For each object, mass and a velocity is super helpful. So mass times velocity give me momentum. I have two objects before, so I'm going to have two momentums before, two masses, two velocities before. I end up with two objects, which means I have two momentums, which means I need two masses and two velocities. So let's fill in some numbers. The mass of the tuber, that's she's referred to as the student versus the hay bale. The student is 80 kilograms, the hay bale is 40 kilograms. After the student collides with the hay bale, what is the mass of the student? Let's hope she's still 80, otherwise that meant she lost something. It is probably more than half if she changes mass. And, so we don't want to talk about that. Okay, so then the hay bale is still going to be 40, assuming the hay bale doesn't go and like explode. But whatever. That's what I don't actually mean kaplow, but like chunks of hay flying. Okay, so there's our masses. The hay bale is sitting in front of a tree, or the bottom of the hill, and the hay bale does in fact stop her. Okay. Now, over here, I call this V2. Is this for the hay bale or the tuber? This is the tuber, right? Now, is this my tuber's final velocity? Or is that my tuber's initial velocity? This is my initial velocity. This is a two-location problem, right? This is also a two-location problem, but this is a different two-location problem than this two-location problem. Just kind of keep that in mind. So this part isn't something super common that I'm going to ask you to do, just for record. It's something we can do, but it's not something we do much of. But that's how fast the tuber is going to start. Or, I'm sorry, not start. That's how fast the tuber is going to be going at the bottom of the hill, which means that's how fast the tuber is going to be moving before she hits the hay bale. And then we're trying to determine how fast that hay bale is going to fly out, which, for the record, is a little bit ridiculous. Like, it's slightly unrealistic, but whatever. So, the fact that the momentum is conserved because it's either it's elastic or partially inelastic, but momentum in all four of these collisions and interactions are conserved, which means I can use this equation. I can say the sum of all my momentum before equals the sum of all my momentum after. That's conservation of momentum. I think this picture really helps build this. So the sum of adding all my momentums before, well, I have two objects at location 1, so I'm going to have to add those two together, and that equals the sum of, I got to add those two things together, my momentum of these two objects afterwards. So I have two objects that I start with, so PA1 plus PB1, sum of, means a plus, momentums of my two objects, I have object A and B, before, at location 1, equals, I end up with two objects, which means I have to have two momentums. I have object A and I have object B, and it's at location number 2, so it's the momentum of those objects at location number 2. Again, two objects, two momentums, two objects, two momentums. Momentum, mass times velocity, so the momentum of A is mass of A times the velocity of A at location 1, because I'm finding the momentum of object A at location 1. This times this. That's why I label it in my picture. Plus, my momentum of object B at location 1, well, momentum is mass times velocity, so mass of B times the velocity of object B at location 1, so mass times velocity, equals, collision happens, the momentum of object A after the collision, well that's the mass of A, times the velocity of A after the collision, plus momentum of B, which is mass of B, times the velocity of B after our collision. It's algebra from here. Setting up the problem, identifying how many objects we start with, how many we end up with, identifying masses and velocities for everything, helps set up this equation, go from here to here, two objects, two objects. How do we find the momentum of this? It's simply taking this times this. How do we find the momentum of this? It's this times this, this times this, this times this. That's all this stuff is. And like I said, from here, we're solving. We have velocities of 0. So that cancels momentum, no motion, no momentum. So it's 80 times 9.90 plus 0 equals 0 plus 40 times VB2. I still have my non-rounded number in my calculator, so I'm going to use that. I'm not going to use 9.8. I'm sorry, not going to use 9.9. I'm going to use 9.89987, whatever that was. So my number is going to maybe be slightly different, but it gives us about 791.6, which is equal to 40 VB2. Divide both sides by 40. VB2 is equal to 19.79 or 8. So about 20 meters per second is about like 40 some miles per hour, 45 miles per hour or something like that. 45 miles per hour. So that hay bale is coming off at about 45 miles per hour. So it's definitely something you want to avoid. But she's also moving at 10 meters per second, which is about 23 miles per hour. So she's moving on the weight on this hill too. This part is from last unit, not super common. This is a two-location conservation of momentum. When I'm dealing with both two different objects for collision or interaction, that's when I use this equation. So, with that, if you have questions, let me know. But the rest of today, about 20 minutes, is work time to work on the worksheet from yesterday called Momentum and Collisions. If you have a question about some of those scientific notation terms and the early part of that with like the Titanic, please let me know. I'll help you with the inputting of those. If you have a question about what equation to use on the front, let me know, but that tends to be the first three equations at the front. Once you flip it over to the back, then we start doing these kind of calculations. Conservation of momentum. I would strongly encourage drawing pictures labeled just like mine. I was helping a student last hour, and they're like, well, we got momentum before, and then I'm like, yeah, but how many objects do you start with? Well, 2, okay. Well, how many objects do you end up with? 2. Well, how many momentums do you have? Well, I only have 1. Right, you're missing 1. Drawing a picture kind of helps visualize and kind of organize that. So I really, really encourage this. It's not because I think extra work is good for you. It's because I think it's good for the problem-solving process. Not like it builds character. It helps you organize your thoughts. That's why I want you to do it that way. So, if you have questions, let me know. I'm happy to help. This is not due tonight. This is due in Canvas tomorrow night at 11:59. So, you may or may not finish this completely today. I had a fair amount of students not finished in my 8-9 class. So I said I probably would give some additional time tomorrow in class. Ideally, just kind of a mental deadline, I would suggest you have this almost done, or done would be great, attempted to be done by tonight, because that gives you the opportunity tomorrow to be like, hey, Mr. Davis, I got stuck on this question, and I want help before I turn this in and I miss the due date. because the due date's tomorrow at 11:59. So that's what I'd suggest. If you have questions, again, I am here, or talk to a classmate, that's fine. Good for learning too.